Every human civilization that ever existed built its calendar around it. Every tide that ever carved a coastline was pulled by it. Every season that allowed a crop to grow did so because of it. And right now, tonight, it is leaving. The moon is not background scenery. It is the only thing keeping Earth's climate from unraveling. Step outside on a clear night and look up. It is there, exactly where it has always been. Pale, full, the same face it has shown to every person who ever lived. It does not look like it is moving. It has never looked like it is moving. But at this exact moment, it is 3.8 centimeters farther away than it was this time last year. It was 3.8 centimeters farther away last year than the year before. Every year of your life, every year of your parents' lives, every year since the first human looked up and felt that the moon was a permanent fixture of the sky, the gap has been growing. The leaving has been happening the entire time. The permanence was always an illusion. Most people who hear this arrive at the same place quickly. The numbers are small, the timescale is enormous, and the moon will still be visible from Earth for billions of years. This is accurate. It is also the wrong question. The question is not whether the moon will still be there. The question is whether it will still be doing the thing that makes Earth livable. And those are two entirely different conditions, and they do not fail at the same time. Earth spins on a tilt. That tilt, roughly 23 degrees from vertical right now, is the reason seasons exist. It is the reason temperate climate zones exist. It is the reason the tropics are warm, the poles are cold, and the band in between supports agriculture, liquid water, and the atmospheric circulation patterns that drive weather across every continent. Without the tilt, there are no seasons, just permanent equatorial heat and permanent polar freeze with nothing predictable in between. With too much tilt, the geometry becomes catastrophic. The poles point directly toward the sun for months, then directly away, turning what are now moderate seasonal variations into decades-long swings between continental incineration and continental glaciation. The tilt is not fixed, it is held. The moon's gravity keeps Earth's axial tilt locked within a narrow range, roughly 22 to 24.5 degrees. That range sounds like a small band, but within it sits the entire history of complex life on this planet. Every forest, every ocean current, every functioning monsoon system, every agricultural civilization that ever fed a human population exists inside those 2.5 degrees of stability. The moon is not contributing to that stability, it is the cause of it. Remove the moon's gravitational influence, and Earth's tilt does not stay where it is. It wanders. Slowly at first, then faster, driven by the gravitational tugs of the other planets, primarily Jupiter, whose mass makes it the dominant gravitational voice in the solar system after the Sun, pulling the tilt in directions that the moon currently counteracts. Planetary simulations that remove the moon's stabilizing effect show a tilt that drifts between roughly 0 degrees and 85 degrees over tens of millions of years. 0 degrees means no axial tilt at all, a planet where the sun rises to the same position every day of the year, where the poles receive almost no direct sunlight ever, where the equator bakes in a permanent overhead sun, and the rest of the planet exists in a thermal gradient with no seasonal refresh, no monsoon cycle, no annual melt that restocks rivers, no climate rhythm that agriculture can track. 85 degrees is the other direction, a planet tilted almost on its side, where the poles face the sun directly for months, where the sunlit hemisphere experiences continuous solar exposure long enough to drive surface temperatures into ranges that no current ecosystem could survive, and where the dark hemisphere simultaneously plunges into months of total absence of sunlight. Between those two extremes, Earth's climate zones would not shift gradually, they would reorganize catastrophically with every swing. Mars has already run this experiment. Mars has no large, stabilizing moon. Its two moons, Phobos and Deimos, are tiny captured asteroids with negligible gravitational influence. Mars has an axial tilt that has varied between roughly 10 degrees and 60 degrees over its history, driven by exactly the planetary gravitational interactions that Earth's moon currently suppresses. The surface of Mars today, frozen, geologically quiet, stripped of its early thick atmosphere, incapable of sustaining liquid water at the surface, is the downstream result of that instability. It is not the only cause, but the tilt variance contributed to the collapse of Martian climate stability in ways that planetary scientists are still mapping. Mars is the direct preview. It is in the same solar system, the same age, the same rocky planet category. The difference between Earth and Mars in this single dimension is the moon. That difference is currently 3.8 centimeters per year smaller than it was last year. The measurement behind that number has been running continuously since 1969. When Apollo astronauts landed on the lunar surface, they placed corner cube retroreflectors, precisely engineered mirrors designed to bounce laser pulses directly back to their source at several landing sites. Since then, observatories on Earth have been firing laser pulses at those reflectors and timing the return trip. The round-trip travel time of light reveals the distance to the moon with millimeter-level accuracy. Over 50 years of this measurement, the recession rate of 3.8 centimeters per year has been confirmed thousands of times. It is not a model projection or an extrapolation. It is a direct measurement. The moon is not theoretically leaving. It is measured as leaving, quantified, confirmed, and exactly consistent with the physics of tidal energy transfer that orbital mechanics predicts. The Apollo retroreflectors transformed the moon's departure from a philosophical concern into a confirmed running process with a verified number attached to it. The number is 3.8 centimeters per year. Over a human lifetime of 80 years, the moon moves roughly 3 meters farther away. Over a million years, 38 kilometers. Over a billion years, 38,000 kilometers. From its current average distance of about 384,000 kilometers, a reduction of roughly 10%. That 10% reduction in distance does not produce a 10% reduction in gravitational stabilizing influence. The tidal force falls off as the cube of the distance. A 10% increase in distance reduces the stabilizing torque by roughly a quarter. A 20% increase reduces it by nearly half. The moon does not need to disappear to stop doing its job. It only needs to weaken past the threshold where Jupiter's influence becomes dominant. That threshold is not a cliff, it is a slope. The transition from stable tilt to wandering tilt does not happen suddenly at a single distance. It happens gradually as the moon's grip loosens and the other planetary influences begin to win more of the contests they are constantly losing right now. The tilt does not jump from 23 degrees to 60 degrees in a year. It drifts decade by decade with increasing variance, producing climate effects that compound on top of each other before any single swing is dramatic enough to identify as the cause. The compounding is where the chain runs. A tilt drift of even a few degrees beyond the current range begins to shift the position of the climate zones, the boundaries between tropical, temperate, and polar regions that determine where rain falls, where ice accumulates, and where surface temperatures support liquid water year-round. Monsoon systems are not driven by heat alone. They are driven by the seasonal differential between land and ocean temperature, a differential that depends on how reliably the sun's angle changes across the year. A tilt that is wandering does not deliver reliable seasonal differentials. Monsoon patterns that currently feed billions of people across South Asia, Sub-Saharan Africa, and Central America depend on the same sun angle returning to the same geometry each year. Remove that reliability, and the monsoon weakens, shifts, or fails entirely in a given region, Not every year, but with enough variance that agricultural planning across generational timescales becomes impossible. River systems that depend on annual snowmelt from mountain glaciers are sensitive to the same mechanism. The glacier accumulates through cold winters and melts through warm summers. The ratio of accumulation to melt determines whether the river flows reliably through the dry season or runs dry. Tilt variance changes the intensity of both the winter cold and the summer heat, not uniformly across the planet, but differentially by latitude. What had been predictable becomes variable. What had been variable becomes unreliable. What had been unreliable becomes catastrophically erratic. At larger tilt excursions, the ice caps begin to respond. Ice reflects sunlight. The more ice covers a polar or high-latitude surface, the more solar energy is reflected back into space rather than absorbed by the ground. This is a feedback. Cooling produces ice. Ice increases reflection. Reflection produces more cooling, which produces more ice. The same feedback runs in reverse. Warming melts ice. Melted ice exposes dark ocean or land surface. Dark surfaces absorb more solar energy, which produces more warming. This feedback is already active in Earth's current climate. Under tilt variance, the polar ice coverage swings with the axial geometry, growing rapidly when a tilt shift moves the poles away from direct solar exposure, shrinking rapidly when it moves them toward it. Each swing in ice coverage accelerates the temperature shift that caused it. The climate does not need a new external forcing to destabilize. The instability feeds itself once the tilt crosses the threshold. The obvious response to this chain is the engineering instinct. If the problem is that the moon is drifting too far, move it back. Future civilizations will have capabilities we cannot imagine. The timescales are vast. Perhaps by the time the stabilizing threshold is approached, humanity will have tools sufficient to arrest the recession. This is where the energy mathematics becomes instructive, not cruel, but clarifying. The moon has a mass of approximately 73 billion trillion kilograms, a number that does not become more tractable when written out. To arrest its recession requires counteracting the tidal energy transfer that is driving it, the same ocean tides that have been moving it outward for 4.5 billion years. The energy budget of that transfer dwarfs the total energy output of every power source humanity has ever built or theorized, combined across any realistic planning horizon. Moving the moon is not a harder version of an engineering problem we already understand. It is outside the category of things to which engineering applies. The actionable knowledge here is not a solution, it is an accounting. Earth's climate stability, the narrow, reliable, agricultural-grade stability that allowed complex civilization to develop in the first place, is not a permanent default condition of the planet. It is a temporary gravitational arrangement. The moon's influence is the single largest factor in maintaining that arrangement, and the moon's influence is continuously, measurably, irreversibly weakening. The weakening is slow enough that no person alive today will experience its consequences directly. It is fast enough that it has run since before the first bacterium divided in Earth's early ocean, and it has already moved the moon far enough that the early Earth, which had a moon roughly 3 times closer and tides hundreds of times more powerful, would be unrecognizable as the same planet. Every centimeter of recession is a centimeter of stabilization surrendered permanently. The Artemis program's return to the lunar surface is framed primarily in terms of resource access and deep space preparation. The retroreflectors placed by Apollo are still there, still being interrogated by laser pulses, still returning data. The data they return is not only the recession rate, it contains information about the moon's interior structure, the deformation of its shape under tidal stress, and the slow changes in Earth's own rotation that are coupled to the same tidal energy transfer driving the recession. Scientists using that data are building the most precise model of Earth-Moon orbital evolution that has ever existed. What that model shows, at every scale it has been run at, is the same thing. The process is monotonic, it does not reverse, and the stabilizing torque is a function of distance that grows weaker every year by an amount that is small, confirmed, and compounding. The question the model does not answer is the one that actually matters. At exactly what level of tilt variance does a civilization need to begin considering that its long-term survival is no longer guaranteed by the planet it lives on? And whether that threshold arrives before or after the civilization has developed the means to leave. That question is currently unanswered. The fuse is currently burning.